Hello students, in this video we'll begin a discussion of covariance and contravariance with respect to two different sets of coordinates on a Euclidean space. Let's be given an initial set of coordinates. Let's call them x1, x2 through xn on Euclidean space. Later we'll do these things on more general surfaces. And then a second set of coordinate changes, right? And a coordinate change. Furthermore, be given a change of coordinates, a one-to-one change of coordinates. So you have the new coordinates. x1 tilde, x2 tilde, xn tilde, right? And when I mean one-to-one, I mean that the Jacobian of this transformation doesn't vanish, right? So what I mean by that is I mean that if I look at the determinant of partial x1 with respect to x1 tilde, partial x1 with respect to xn tilde, partial xn with respect to x1 tilde, partial xn with respect to xn tilde. If I look at this determinant over here, the determinant is not 0, at least locally in some neighborhood over here. In other words, I'm allowed to invert these transformations over here. Now it turns out that when you have this determinant condition being non-zero, that says that the inverse exists. In terms of the inverse exists, the inverse is going to be one coordinate instead of the other. That's what it means to be one-to-one. You can go back and forth from one to the other. And the inverse of this matrix, you just simply take the reciprocal of all these differentials, right? So that makes it really nice, easy, beautiful, okay? And so now what we're going to do is we're going to do this. We're going to define, so here's our definition. So two coordinates, I can go from one coordinate to the other and one to the other, vice versa, right? And so we say, definition, we say that a collection Ti, lower, I goes from 1 to n, form a covariant one tensor if I'm going to write this as Tj tilde. Tj tilde is going to be Ti, and then partial xi, partial xj tilde like this, okay? Now, what I'm doing over here is I have an I over here and an I over here, which means I'm summing over I. So what this really means over here is that this condition over here means that j is fixed and I'm summing over I, so this is really just the sum. It's really just the sum over I of Ti and then partial xi, partial x tilde j. Now also it's important to note here that I've suppressed other notation. I've suppressed the fact that these Ti are really functions of x1 through xn. And that means they're also functions of what? They're also functions of x1 tilde through xn tilde, right? And Tj tilde are functions of x1 tilde through xn tilde. Okay? Excellent. And of course we have these xn tildes in the denominator over here, which means that these are genuinely functions of the xn tilde. So I'm giving you telling you how these functions over here act with respect to a coordinate change. Okay? That's what it means to be a covariant one tensor. I can do the same thing for contravariant tensors. So that's the next definition, and we'll try to unpack this. We say that's a collection. Now I'm going to use upper indices, b, I goes from 1 to n, form a contravariant one tensor if what? If Tj tilde, I guess I said b over here, so I'll say b, not t. If b j tilde in the tilde coordinates are equal to bi, and then xj tilde over xi, like that, okay? So this is the criterion to be a covariant tensor. Notice how the tildes are in the bottom. And this is the criterion for being a contravariant tensor. Notice the tildes are on top, right? So they refer to things how we're going from one coordinate frame to another coordinate frame, okay? Now, these, of course, are one tensor. I can basically take this and make this and turn this into a higher dimensional setting. But before I do that, let me give an example of how we can transform from these definitions to the other. So now this is exactly equivalent. So what I'm going to do now is I'm going to do a very common thing over here. I'm going to hit both sides of this with partial xi, partial xjk, x tilde k, like that. And then I need to hit this with something different. So I want to do something a little bit different, actually. So I'm going to be a little bit careful about this. I'm going to hit both sides of this with a partial xj tilde in the denominator. So I'm going to do a partial xk, partial xj tilde to both sides, to make sure the indices are in the right order, to the b tilde j is going to be equal to what? It's going to be equal to bi, and then partial xk, partial xj tilde, partial xj tilde, partial xi. And now these matrices are inverses of each other over here. So what this turns into a bi, and then this is going to be a delta ik, delta, and then k on top, and then I on the bottom. And so this just turns into forcing I to be k, so this turns to bk. So in other words, this condition over here, this contravariant condition, is exactly equivalent to what? Is exactly equivalent to saying that bk is equal to what? Is equal to bj tilde, and then times this expression over here, partial xk, partial x tilde j. So in other words, those conditions are equivalent to each other for being contravariant. So of course, it depends on where you put the tildes relative to the expression to make it work, right? We can do the same thing over here in terms of multiplying everything over here by a delta tilde of xj over xk, right? And so we'll get the same exact expression over here. So the idea now is that let's try to uncover why this relationship works over here, why there's this inverse relationship over here. So let's think of an example, the classic example. The easiest coordinate change is that x is equal to r cosine theta and y is equal to r sine theta, right? And so let's look at these matrices from the context of the x's. The untilde x's will be the ordinary x's. So if I want to look at this matrix over here, x tilde k, x tilde j, like this, would be what for this matrix over here? It'd be the derivative of x with respect to r. That's going to be a cosine theta. Derivative of x with respect to theta for the next entry over here, that'd be a negative r sine theta. Then the derivative of y with respect to r would be a sine theta. And then derivative of y with respect to theta would be an r cosine theta. So that'd be my x tilde, xk, xj tilde. What would be the opposite matrix? What would be my x tilde what? My x tilde j, x I, like that. What would that give us? That matrix over here would be the derivative of r with respect to x, right? And so of course, let's solve for r. So r is equal to the square root of x squared plus y squared. And theta is equal to the inverse tangent of y over x, right? Okay. And here's where we have to be very, very cautious about our constrained partial derivatives over here, right? So we want to be very, very careful that these are now treated as the independent variables over here. So this is going to be r with respect to x is going to be an x over the square root of x squared plus y squared. The y is going to be y over the square root of x squared plus y squared by symmetry. The x derivative of theta is going to be what? It's going to be negative y over what? Negative y over x squared plus y squared. And then the x derivative, or the y derivative of theta, is going to be an x over x squared plus y squared. And you might look at these matrices and say, well, geez, when I multiply these matrices together, what's going to happen? Well, let's check and see what happens. So if I did the row dot column over here, I'd have an x cosine, so that's going to be an r cosine squared. That's going to be an r sine squared, so that's going to be a what? That's going to be an r squared, basically. So I have an r squared over what? Over, so let's see, let's do this carefully, actually. So let's make sure we're getting everything correct over here. Good, there's an r squared in the denominator, so it's homogeneous in the right order, right? So over here, what we have, we'll have a r cosine squared. Over here, we'll have another r cosine squared, r sine squared, that's going to add to 1, and everything cancels out. So if we multiply these matrices together, what are we going to get? So multiplying these matrices, let's check the other things over here. If I do row dot column, I'll have an x with a negative r sine, and then a what? And then a y with an r cosine, so those are going to cancel out. And then those terms will cancel out, and then in the bottom terms we'll get the exact right order over here. So when you multiply these matrices together, so this matrix, let's call this matrix over here A, and this matrix over here, let's call that B, then it's easy to see that A times B is equal to B times A is equal to the identity, right? And so in other words, this just follows from the chain rule. The chain rule tells me that these matrices over here have to be the inverses of each other by the fact that if I go from x to the x tilde coordinates and back from the x tilde coordinates to the x coordinates, I have to revert back to the original x tilde coordinates. When you differentiate that using the chain rule tells you that those two matrices have to be inverses of each other. So in other words, we get the algebraic expression that we want. That in other words, if I was just simply to take the reciprocal of these differentials, I would have the exact right form. The only thing to be careful about is we want to make sure we preserve the indices in the right order. So if I have an xi over here and an xk over here, I don't want an xi and an xi, because that would be summing over I, and that's a little bit different over here. So when you sum over j is when you get the inverse, because you're doing row dot column, row dot column, row dot column. So you have to preserve the matrix multiplication structure over here. But it's important to realize that there's going to be writing the definition of contravariance and the definition of covariance all depends on the location of the indices and making sure that the differentials and the coordinate changes are in the right direction, right? But again, it's always relative to an initial set of coordinates, right? So making sure that you carefully follow the definitions for what your initial set of coordinates is relative to your coordinate changes will help you understand this definition of one covariance versus one contravariance and see how we can generalize that to higher dimensional tensors, which you'll see in further videos. Thank you very much.